Welcome back, ladies and gentlemen. Today we're going to talk about something called the Squeeze Theorem. Now, yesterday we had talked about a little bit about this little guy, sine x over x, and I asked you, or I actually just told you the limit was 1. And you could have come about that any number of ways. You could have graphed it, and it's pretty obvious from the graph that it does indeed achieve a height of 1 at an x value of 0, so that's reasonable. You could look at the table, and you could establish a pattern within the table of values that they're tending towards 1 from both sides, but neither of those is actually a proof or an algebraic way to get there. And today what I'm offering is just that, an algebraic way to prove a function has a limit when we can't do it algebraically otherwise. There's a lot of ways to evaluate limits, but this just expands the horizon just that little bit more. So today what I'm going to do is I'm going to walk you through the proof of why the limit of sine of x over x is equal to 1 using a technique called the Squeeze Theorem. And then I'm going to expand upon that and show you how to do it with a few other functions. Okay, so firstly, what is the Squeeze Theorem? The Squeeze Theorem is, there's not much we can say about this function right here. It's difficult to say intelligent things about that algebraically. However, if we're lucky, we can set up one of these limit problems, and this is a different example, but we can set up a problem in such a way that we can compare the function that we care about, that would be this pink function right here, and it's defined right here, and we can squash it in between two functions that are hopefully simpler, or at least we know more about. So in this case, this more complicated trig function was sandwiched between two parabolas. And by doing that, it forces the unknown limit, the unknown function, into an infinitesimally small point. And we can therefore assume that the limit is the same as the limit as the parabolas. So here it is written out in words, and it's in your book. I don't think you need to write it down. This is from Wikipedia, and they use the letter I in math. I don't know why you would ever choose to use the letter I, but here it is in words. And I'll explain it in English in just a moment, but let I be an interval having the point A. So the point A is where we're going to evaluate the limit as a limit point. Let G, F, and H be functions defined on I. So they give you an interval, and they just want to make sure that all three functions, G, F, and H, are all defined on I, except possibly at A itself. And it's okay for it not to be defined at that little spot, okay? Anything other than that little spot, you got a problem, okay? Suppose that every x in I not equal to A, so everything except A, we have this behavior, okay? So first off, we have a sandwich, okay? We have been able to successfully sandwich the function that we care about, that one, between a high and a low. So the top function and the bottom function sandwich the function that we care about. Secondly, we need the top function and the bottom function to achieve the same numerical limit. They have to have a limit, and it has to be the same limit at the x-coordinate that we care about. If all of that is true, we can conclude that the limit of the middle function, the meat of the sandwich, is the same as the crust. So I wanted to do one that's a little bit out there with the sine x over x. So we're actually going to explore this unit, the limit as x approaches 0 of sine x over x. And I have told you that the answer to that question is 1, but we haven't actually proved it yet. So what I'm going to do here is I'm going to set up an actual geometric proof, and I'm going to show you how to work it from there, okay? So I have a drawing here on the unit circle. So this is the first quadrant of the unit circle, where this is our radius right here, a distance of 1. So it's important that we're on the unit circle so that we know that that distance is 1. That simplifies the area calculations that we're about to do. So what we're going to do is we're going to express the area of a triangle, a sector, that's like a slice of pizza, and another triangle. So we can see that we have an outside triangle, that's the biggest shape. We have a sector, not that. We have a sector where our slice of pizza is right there. And then we have an inner triangle, okay? And no matter how big that angle is, one thing will be true. The small triangle will always be the smallest shape, the sector will always be the middle shape, and the large triangle will always be the big shape. Okay, so I'm going to clean up my drawing here a little bit. And let's go through and let's calculate some of these. One of the things you may not remember is the area of a sector. The formula is right here. I'm going to skip all the way down to the bottom here. Okay, 1/2 times the radius, which, because we're on the unit circle, is 1. Square that times theta. And we don't know what theta is. That's like the x up in our limit statement up here. So theta is x. As long as we're cool with that, we can move on. So that means that this is theta over 2. So the area of the pizza slice, the sector, is theta over 2. The second one that's pretty easy to get is the small triangle. So triangle ABC, the middle one on our screen here. And I'm going to need a height of that triangle. So if I drop that down right there, you'll notice that that height is sine theta, because we're on the unit circle, which means that the area of this triangle is 1/2 times its base. Its base is 1 because it's the radius of the circle, and its height is sine theta. So that means that the overall area of this is sine theta over 2. So we have one expression that's pretty simple. We got another expression that's pretty simple. It would be awesome if the third expression was also simple. But I don't know how to calculate the area of that triangle so good. But here's something very coincidental that we can use. Let's try to figure out the tangent of theta using the blue triangle, ADB. Well, in that case, it would be true this distance right here is the opposite side from the angle, and this distance right here is the adjacent angle. So I'm just going to write that down. I'm going to say that the tangent of theta is equal to the length of the opposing side, that AD, as it were, over the adjacent side. Now, the adjacent side just happens to be 1. So what that means is that tangent of theta equals the length of the opposing side, or AD, because this is equal to 1. So now I have this statement that tangent of theta, this distance AD over on the far right here, is equal to the opposing side. So tangent theta, or the opposing side, is equal to tangent theta. So that means that I can write the height of the triangle in terms of tangent theta, or I can write it in terms of theta rather than introducing another variable. So the area of this triangle is 1/2 times its base, which is also 1 still, right? Because it's still this distance, AB, right there. And then times the height. And the height we just figured out was tangent of theta. Okay, using this equation right here. That's the height of that blue triangle. And if we just simplify that a little bit, we get another fairly simple expression. And there we go. Okay, so we've got big, middle, and small. So the small triangle will always be small. The sector will always be in the, or, well, sorry, I'm doing this wrong. Sorry, this is our small bit right here. This is our small triangle. And our sector is in the middle. Okay, so let's make that more clear. Let's list them from smallest to biggest. Okay, so I'm going to zoom out here as soon as my page stops moving around. Okay, it's not going to do that. Okay, so anyway, I'm going to go with theta over 2. And I'm going to write an inequality that I know to be true. This is the start of all squeeze theorems. You have to squeeze. You have to build the sandwich, okay? So we know that the big thing is tangent over 2. So I'm going to go tangent over 2. And I know that the small thing is sine over 2, sine theta over 2. Now, here's the problem, is that I want, this inequality doesn't do me much good. I want sine theta over theta in the middle. I want this in the middle of this inequality. So here's what we're going to do. You notice that there's a 2 on the bottom of everything. So let's multiply the whole thing by 2. No big deal there. So then I have sine theta less than theta less than tangent theta. All right. Then I'm going to do a little something weird. I'm going to divide. You'll see where it's going. It's not intuitive necessarily, but I'm going to divide by sine on all 3 of these as well. And you can see now in the middle I've got the reciprocal of what I want. That's the purpose of doing that. Sine theta. And if you take tangent of theta divided by sine of theta, you get 1 over cosine of theta. So over here we get 1. Over here we have the reciprocal of what I eventually want. Okay. And then I have 1 over cosine if you simplify that. Write out tangent as, remember, tangent is sine over cosine. And the sines will cancel, and this will have a 1 over the cosine. Okay, now here's a trick about inequalities that you may not know. If you reciprocate everything, you just switch the order of the inequalities. So if I reciprocate, that is, make numerator denominator and vice versa, if I reciprocate 1, I get 1. I'm going to change the direction of the inequalities as I do this. Then I'm going to go sine theta over theta. So now I have what I want in the middle. That's important. And over here I have cosine of theta. So here's the cool part. I'm just going to rearrange this from left to right again, from smallest to biggest. So now my small end is on the right, actually. So I got cosine theta less than or equal to what I care about, sine theta over theta, that's sine x over x, and less than 1. So more or less, I've squashed the function that I care about in between 1 and cosine of theta. Now, here is the calculus part. We are going to say, okay, I know this is true, and now I'm going to apply a limit to figure out what happens when, not x, theta approaches 0. Now, if I take cosine of 0, okay, that is evaluable, so I can get that. That is 1. Less than or equal to, I don't know. This is a problem. This is an undefined function right there, so I don't care about the middle. I don't have to do that. But the other side is also 1. Now, if I have an inequality where I've sandwiched two things between 1, well, what must the middle thing be? It must also then be 1, okay? So then my conclusion, therefore, the limit as theta approaches 0 of sine theta over theta is equal to 1. Just as we said, just as our graph suggested, and just as our table suggested. They all work. Okay, well, now that we've actually proven it, now we know this, and just like I said before, this is something that we want to memorize. But I want to show you that we can build off of this one little thing into grander things. So the next one I actually want to show you is right here. This one we're actually going to use an entirely different technique. It's actually not related to what we just proved, but it's going to get us a second result that is something that you're going to want to memorize because they're going to do variations on this little guy right here. Okay, so take a moment, copy down that problem, and I'll show you how to get this one done. This one is very similar to if you had a square root in the problem. You see this two-term thing with a minus sign in between, and that's oftentimes an indicator that you want to use a conjugate. So that's exactly what we're going to do. We're going to write down the exact same thing. We have not taken the limit yet, so we don't want to drop that symbol until we take the limit. That's super important as you answer FRQs. We're going to take the original thing, 1 minus cosine of x, okay? And we are going to multiply it by the fancy version of 1 plus cosine of x over 1 plus cosine of x. And that still has an x on the bottom. So all I'm doing is multiplying it by 1. But here we go. If we multiply these things together, we square the first term, so we get 1, and then we keep the negative, but we square the second thing as well. So it's cosine squared of x. And on the bottom, I'm not going to multiply that out because I oftentimes don't have to in these problems. Sometimes you do, sometimes you don't, but usually it's a no. All right, so now we have that. And hopefully this is setting off little alarm bells right here, this phrase right here. If you took our Pythagorean identity, which is sine squared plus cosine squared of x, and you rearranged it, you would get that top section equal to sine squared of x. Okay, so now I have that going for me, and I can build up that fraction again, x, 1 plus cosine x. Still got the limit symbol out there because I haven't done that yet. And now that we have it in this form, we can break it up. So you may notice that there is a sine x over x in here. So I'm going to break it up into sine x over x times sine x over 1 plus cosine of x. And hopefully now we can plug in a 0 and get an answer. Okay, so we know that this limit goes to 1. So I have 1 times the limit of whatever this is going to be, x approaches 0, of sine of x over 1 plus cosine of x. So hopefully we don't get 0 over 0 in indeterminate form here. I don't think that'll happen. We'll have 1 times, you plug in 0 on top, you get 0. You plug in 0 on the bottom, right here, you get 1, so you get over 2. And 1 time, so we got 0 over 2, which is 0. 1 times 0, which equals 0. Okay, so we have a second result. And this one's used enough, and this one is used enough to go about memorizing it again. So there are 2 results that I'd like you to memorize from today's work. Okay, next up, I want to show you how some of this can be used in a little bit simpler problems. Check this one out. You should recognize that it looks like something that we just did. Okay, so this is almost sine x over x, but it's got a 10 in there. And it doesn't really matter what number they throw at you up inside of that sine function. You just want the same thing. It would be really nice if the same thing was right there, because then the answer would be 1. I don't think it's that simple. Okay, so we're going to have to introduce a 10 to make that work. Okay, so in order to introduce a 10, I'm going to multiply everything by 10 over 10. Okay, I'm going to multiply everything by 10 over 10. I'm going to leave the numerator on the outside of the whole expression, but I'm going to bring that denominator in. So I'm going to bring the limit as x approaches 0. Remember, this is a property of limits that we can move constants in and out of the limit notation. It does not matter. And I have 10x. So now I have the same thing. So this whole limit right here, this is sine x over x basically. It's just 10x. That's 1. So then I have 10 times 1, which equals 1 for our final answer. And you can use that sine x over x to answer more and more complicated things. Next one, let's take a look at this one. Now this one doesn't have a sine x over x, nor does it have a 1 minus cosine x over x. So this one is written in terms of tangent. Let's see what happens when you write tangent in terms of sine and cosine. Limit as x approaches 0 of sine x over cosine of x over x. Okay, so that would mean that we have, if you're good with fractions, and not everyone is, that's basically the same thing as this expression coming up here. We have a 1 over x, because that x was on the denominator, it still is, and this is multiplied by this fraction, if that makes things a little easier. And then you should be able to see we have that sine x over x very clearly there. So we have limit as x approaches 0 of sine x over x times 1 over cosine of x. This piece right here goes to 1. And if we plugged in, so if I do a direct evaluation, if I just plug in, well, we know this limit is 1. And if we do direct evaluation on the other thing, cosine of 0 is 1. So over here we get 1 over 1. So basically we have 1 times 1, which equals 1. Okay. All right, next one. I'm going to show you how to do a squeeze theorem problem from scratch. Take a moment, copy this one down. Here's how you do a squeeze theorem problem. You start by writing down an inequality of known information. Okay, so I don't know much about this function, but I do know a lot about the function sine of 1 over x. And remember, that's that weird function that oscillates an infinite number of times on a graph. And if you want to, it's actually it's interesting to look at this whole thing on a graph if you want to take a moment and just pause and graph that on Desmos or graphing calculator. It's a cool looking graph. But anyway, what we have to do is write down an inequality of known information. And like I said, I know a lot about the sine function, no matter what's inside of it. That's important. No matter what's inside of that sine function, I know that that sine function is trapped between an upper limit of 1 and a lower limit of -1. That's how I just created a sandwich. That's always step 1. And then we're going to squeeze and squeeze and squeeze until it's the same number. Okay? Now what I have in the middle does not match what I want. I want x times that expression. So if I take and multiply the entire thing times x, I can get there. So go negative x less than or greater than x sine 1 over x. Now I have what I want in the middle, which is good. And here's x. And then finally, for our last trick, we have to reach into our newly developed calculus skills here, and we have to apply a limit to the entire inequality. Now when you plug in 0 there, you get 0. We don't know what this is, but we do know what this is. That is also 0. Therefore, since the top end is 0 and the bottom end is 0 and the two are always in between each other, or it's always trapped on top and bottom, therefore, the limit as x approaches 0 of x sine of 1 over x, and it doesn't matter what's inside there, will also equal 0 as our conclusion. Let's do one more. Take a moment, write this one down. Again, we have a fairly complicated function, but we have a piece of it that we know a lot about, where we can create an inequality of a sandwich. I'm going to take that cosine expression, cosine 3 over x, and I'm going to sandwich that between a positive 1 and a negative 1, because I know whatever is inside that cosine function, the whole thing is trapped between negative 1 and positive 1 the whole time. Now you see there's two more elements that I need to add to the middle, or incorporate into the middle, that I don't have yet. I need to add 2 and I need to multiply by x squared. Now if I added 2 first, then I would multiply everything, including the 2, by the x squared later. So I'm going to first, order of operations matters here a little bit. We are going to first multiply x squared times everything. Doing that, we will get negative x squared times cosine of 3 over x less than or equal to x squared. And then we want that plus 2. Okay, so we'll tack on a plus 2 to everything. So we'll add 2. See where that ends up. So we got negative x squared plus 2 less than or equal to x squared cosine of 3 over x plus 2. That's what we want in the middle. That's good. And we have an x squared plus 2 here. And lastly, we were asked for the limit as we approach 0. So we're going to take the limit of this whole giant thing as x approaches 0. And we don't have to worry about the middle, which is kind of nice. But if we go to 0, that goes to 0, but it ends up with 2. That goes to 0 as well, but we also get a leftover 2. So this is good. The left endpoint is 2. It's sandwiched between, well, we don't know what the answer is here. We just know that it's the function that we care about. And the right-hand side, or the top end of the sandwich, is also a 2. So therefore, we can conclude that the limit as x approaches 0 of x squared cosine of 3 over x plus 2 is equal to 2. That's all I have for you today. I'll see you next time.